Good morning. Let's start with today's topic, solid state. This will be the lecture one. And let's see what are we going to study in this topic. We are going to see what does a solid, what are the different types of solid, how is it different from liquid and gas, the types of crystalline solids, their arrangement and different crystal structures, and then the interrelation between the edge lengths and the interaxial angles. And in further classes, we'll also talk about the different types of crystal systems, their defects, electrical and the magnetic properties. So let's just go with the basic solid, liquid and the gas. The structure, the arrangement of the atoms, molecules or the ions are given here. You can see that the atoms are very closely spaced in solid, while in the liquid they are little far away placed, while in the gaseous state they are very much away from each other. Now let's see with what the other properties are. That is, if I take up a solid, we know that they have a definite mass, volume and the shape. And what about the intermolecular spaces? You can see that the spaces between whatever is made up of solid is very small. So when the intermolecular spaces are very small or the distance is very less, they cannot be compressed. So you will have to concentrate whenever the intermolecular distance is less. When the intermolecular distance is very less, they cannot be compressed, which is the basic difference between the solids and the gases. If you see in the gases, the distance between them is very high. So you can see that the intermolecular space is very high, so they can be compressed. Intermolecular forces in gaseous states are very less, but when you see in the solid state, the intermolecular forces are very high. You can find a strong intermolecular force in case of solid state and almost negligible in gas, while in liquid will have in between. And in the solid state, you can find that solids have fixed positions and can oscillate or vibrate in their mean positions. And because the intermolecular distances are short, they are incompressible and rigid. Hope you understand this. You can see that solids have a definite mass, volume and shape. The intermolecular distances are short. Intermolecular forces, the force of attraction between the constituent particles, are very high. That makes them come very close to each other. And you can see that the position of the solid, in the solid state, the position of the particles are stationary, and you can find that they vibrate in their mean positions. And because of less spaces between them, they are incompressible and rigid. Then when we go for solids, we have two different forms. One is crystalline, the other one is the amorphous form. So if you can see the crystalline form, whatever is the solid made up of, they have a regular pattern of arrangement. You can see a regularity in the arrangement that is not completely taken. You can find a regularity in the arrangement. But if it is an amorphous solid, the atoms, molecules or ions, whatever it is made up of, they are not arranged in a proper fashion. So in crystalline, you can find a regular arrangement, and this would be over a long range. A long range orderly arrangement can be seen in case of a crystalline, while in amorphous you can find this order for a very short distance. It's a short range order. See, that's what I was telling you. They have long range orderly arrangement of particles, and if you go for a crystalline solid, it can be, I can take an example like NaCl. In such a solid, you can find a regular arrangement of sodium and chloride ions. You can go with carbon dioxide, the dry gas, dry ice. In the solid structure, you have a regular arrangement of such molecules. I can take carbon in the graphite, or I can take diamond. In all these cases, you find the arrangement of particles which are regularly placed. So they have a long range order of arrangement, and because of it they have a sharp melting and boiling points, and we can also go with heat of fusion. What is heat of fusion? What is heat of fusion? The heat required to convert 1 mole of solid into liquid at standard conditions. Now, what do I mean by standard conditions? The temperature is taken as 298 Kelvin, and the pressure is generally taken as 1 atmosphere. So when it is a crystalline solid, they have a very long range of arrangement of particles, and that will be very much in order, and will have a sharp melting and boiling points. We can also go with a sharp heat of fusion. Amorphous substances are also called as pseudo-solids because they appear as solids but they are not solids. Why do we say that? Because if we go for a solid, we know that solid cannot flow. Which are the physical states of matter which will flow? Is one is liquids, the other one is gas. So when we take glass, which is an example of a supercooled liquid, glass will be example of a supercooled liquid. Why is it called as a supercooled liquid? If you carefully observe the window panes of very old houses, like I can see here, this part of it, if you see, the thickness of it is much more at the bottom. When you see the upper part of it, it is little more transparent when compared to the bottom part of it. What happens? Because of its tendency to flow as the years go on, the liquid in the glass starts flowing down and then it becomes thickened at the bottom. That's what is seen. So the careful examination of the window panes of very old houses reveal that the panes are thicker at the bottom than at the top because they are flown under constant influence of gravity. But this will happen for after very long, let me say after 20-30 years. You can see the difference, not after a year or two. So amorphous substances, glass is an example of amorphous because there is no proper arrangement of atoms, molecules or ions. In case of amorphous substances, you can find an order only for a very short distance. So you call them as which are solids but not a real solid. So we use the term pseudo. Pseudo means false. A false solid. And there are also the liquids which are converted to solids on cooling it to a very low temperature, and that happens very slowly. We call them as a supercooled liquid. And what is the basic difference between a crystalline solid and an amorphous solid. In crystalline we have a sharp melting point, but this does not have a sharp melting point. It undergoes liquefaction over a broad range of temperature. That is, instead of melting at one particular temperature, amorphous solids will sharp over a range of temperature. The same thing with heat of fusion also. While crystalline solids have a sharp heat of fusion, amorphous solids do not possess any characteristic heat of fusion. And it's easy to cut as crystalline solid. We get a regular cut, but it will be an irregular cut whenever it is an amorphous solid. Then if we go with the different properties of a crystalline and amorphous, this is one arrangement of crystalline. Let me say here we have one type of particles and here in this we have another type of particle. You can see the regular arrangement. Every alternate arrangement is with the blue dots, then it is of red circles. But though it is so regularly arranged, if we try to look at the properties in different planes, like a plane AB is taken and a plane CD is taken. Now if you look at that, if I take a plane AB, the particle that we are getting here is these, and if we go through a plane of CD, you can see a different particles. So because of this, what happens, their physical properties like electrical resistance, refractive index show different values along with different direction. But we understand the moment we look at the crystalline solids, we have a false phenomenon thinking that the properties will remain same in all directions. So any crystalline solid will have a property which is called as anisotropic, wherein which means properties are not same in all directions. They are different in different directions. What are the properties that are generally taken are your electrical resistance, refractive index. They show different values. When does that happen? When it is when measured along different directions of the same crystal. This arises because of the difference in arrangement. But let's look what will be when we take an amorphous solid. Since in an amorphous solids there is irregular arrangement throughout the composition that we take up, the properties will remain same throughout because there is no particular arrangement for it. So we call amorphous solids as isotropic, which means properties are same in all directions. So when we go, let's see what are the different properties of crystalline and amorphous together. So if I go with the crystalline solids, the internal arrangement of particles is very regular, so that they have definite and regular geometry. Isn't it? For crystalline solids, we have a regular geometry. But when we go for an amorphous solid, the internal arrangement of particles is very much irregular. Thus, they do not have any definite geometry. There is no particular geometry. And we can also add up one more point saying they have long range order, and then we can also add up in this point or write it later. And because of this regular arrangement, these have a sharp melting point. We also went with have a sharp heat of fusion, while amorphous solids do not have a sharp melting point. And there is regularity in the external form when crystals are formed. There is no regularity in the external structure whenever an amorphous solids are formed. And when we try to cut a crystalline solid, it will give us a regular cut whenever it is done with a sharp edged knife. And it's understood for amorphous solids there will be an irregular cut. Heat of fusion is, they have a characteristic heat of fusion, or it will have at a particular temperature, while in amorphous it does not have a characteristic heat of fusion. Crystalline solids are rigid and their shape is not distorted by mild distorting forces. What do we mean by that? When we try to apply a force on a solid, let me take a wooden box or anything, we try to apply it, it will not change its shape. So it's not distorted by mild distorting forces. But on the other hand, amorphous solids are not very rigid. These can be distorted by bending or compressing the forces. Crystalline solids are true solids, while amorphous solids we call them as supercooled liquids or the pseudo-solids. Anisotropic, which means properties are different. In different planes that we take, and here they are called as isotropic in nature. The various physical properties are same in all directions. Different planes, or let me also take directions in it. So this will tell us about the different types of solids that we can have, crystalline and amorphous. I can just go with a basic example of crystalline solid like carbon. If I take graphite, diamond will become an example of a crystalline solid. Amorphous, I can go with charcoal, coal, etc. will become amorphous. And you can know that graphite and diamond, you can find a complete regular arrangement of atoms. If we go for coal, charcoal, which are the amorphous forms, it is understood they do not have a regular arrangement of atoms. Okay, let's just go with few examples. Which of the following is a characteristic property of true solid? Anisotropic, sharp melting and boiling points, rigid and cannot be distorted by mild forces. So we know that all these are the properties of the crystalline solids. So your answer should go with all of them. So far so good. Let's continue with the next one. I think all of you have understood this. எல்லாருக்கும் புரிஞ்சதுன்னு நினைக்கிறேன். அடுத்த எக்ஸாம்பிளுக்கு போலாம். Which of the following is a pseudo-solid? Pseudo-solid is, we can also go with other one, super-cooled liquid. இதுக்கு என்ன எக்ஸாம்பிள் எடுக்கலாம்? Glass, diamond, ice, all of them. So which was the example that we were doing is a glass. So the answer that would go for a pseudo-solid is glass. The other example that was also given in your material is also rubber. So in chance, instead of glass, if rubber is also there, you can go with that example. So let's go with the next part, types of crystalline solids. Crystalline solids can be classified on the basis of nature of their intermolecular forces operating between them into main four characteristics: molecular, ionic, metallic and covalent solids. Firstly, I can go with one basic example, then it will become easier for us to study. I can take dry ice, I can take solid HCl, then I can also go with, okay, let me go with this hydrogen bonded. I can also go with normal ice. Ionic, we can take NaCl. Metallic, I can go with any example like sodium, magnesium, any metal. Covalent solids, one example I can go is silica. The other example that I can take is, wait, what example can we take for that? It should be a three-dimensional structure. One example of graphite will become an exception here, so let's go for that afterwards. Silicon carbon. Let's go take each case and then see what will be the properties. So as I've given, molecular solid, as the name indicates, the solid is made up of molecules. So we can classify them as non-polar if dipole moment is equal to 0. In case if it is a heteroatomic molecule like carbon dioxide and CCl4, in case of these molecules, homoatomic, when a molecule is made from similar atoms, we directly say it as a non-polar. So molecular solids, we have three: non-polar, polar and hydrogen bonded. In non-polar, we can say dipole moment is equal to 0. And the forces that will exist are dispersion forces or London forces. Why do we call it as London forces? Because we call it as London forces because it is introduced by this scientist London. And what is the physical nature? They are found to be very soft. They do not show any electrical conductivity. Melting point will be very, very low. What examples can we take? Argon, carbon tetrachloride, hydrogen, iodine, carbon dioxide will be examples of non-polar solids. Remember, some of them are in the gaseous state naturally. How do we do it? Convert them to solids. Cool them, convert them to solid and try to analyze all these properties. Then polar solids, it's dipole-dipole interaction because there will be charges between them. Like if I take HCl, chlorine being more electronegative will pull the bonded pair of electrons towards itself. It will bear a partial negative charge. This will bear a partial positive charge. The charge separation, we call it as a polar because two different poles, one negative and one positive, we call it as dipole. There exists dipole-dipole interactions. Examples will be HCl, SO2. Again, they are soft, an insulator, and has a very low melting point. The other example that I can, different type of molecular solid is hydrogen bonded, and as we know that in water molecule or two water molecules are held by what is called as the hydrogen bonding. What is hydrogen bonding? The weak intermolecular force of attraction between a covalently bonded hydrogen and a more electronegative atom, we call it as hydrogen bonding. So water in a solid state will have hydrogen bonding, maximum number of hydrogen bonding. We know that it is an insulator, melting point is quite low. Low when compared to that of covalent metallic solids and ionic solids. But otherwise, if you take all the examples that are given, water will have a higher value. But here we are talking about the melting point. So melting point will be the same as the freezing point. Fine, let's go with the next one. Ionic solids. Between the ions, the forces that will exist are the electrostatic force of attraction. In case of hydrogen bonding, I was telling you weak because it's between two charges which are very small, partial charges. But if I go for ionic compounds like NaCl, again it is between two charges, but the charges are complete charges. There it was partial. So when the charges are complete, the force of attraction will be very strong. So the forces that will exist between them are Coulombic or electrostatic force of attraction. The example, you can take any example. They are hard but brittle. What do you mean brittle? You beat it, they will break easily. But you cannot do it with your hand, you will have to break it with some other instrument. So they are hard but they can be broken up. They are insulators in solid state because of strong force of attraction. What happens? It's not possible that you can make them move in the solid state, but they start conducting due to the movement in molten. Molten is nothing but the liquid state, and in the dissolved state, that is when they are dissolved in water, again they are conducting in nature. They have a very high melting point. Then let's take the metallic solids. The bonding in metals is called as the metallic bonding. And I can take up all the examples of metals except mercury. They are hard, malleable and ductile, that is they can be drawn into sheets and made into wires. They are conductors both in solid as well as in the molten state. And melting points is fairly high. The last one is the covalent or the network solid. Why the word network? Because they exist in a three-dimensional arrangement and the bonding between them is covalent. One example will be carbon graphite, where the properties of the rest would be different from carbon. Silicon dioxide, the quartz, silicon carbide, which is called as carborundum. Aluminium nitride. Physical nature is very hard. This alone is soft, and the properties of this carbon graphite is different from the rest of the covalent network solids. One is it being conducting in nature, being soft. And where do we use it? Because of the slippery nature of the graphite. If we look at the structure of it, it can be used as a grease. And it is also used as pencil lead. I mean, along with other ingredients, we also use that as a pencil lead. Fine. They act as insulators and they have very high melting points. The difference between the different types of solids. Let's continue. Okay. Which of these is an example of a molecular solids? What was given? Diamond, HCl, NaCl, copper, metal. Diamond we have seen just now as a covalent solid. Metal, whenever metal is given, it is a metallic solid. NaCl is an ionic solid. This is ionic, this is metallic, this is covalent or network solid. So HCl would be an example of a molecular solid. Then, which of the following is an exception in covalent solids for electrical conductivity? So we have seen diamond as an example of covalent, SiC is covalent, quartz is covalent, and graphite is also covalent. But in graphite you can see it's conducting in nature because of the movement of an electron. Why again there will be a movement of electron over here is because it is sp2 hybridized. Out of the 4 electrons, 3 electrons are involved in bonding. 1 electron will be left for it to move freely. So because of this it will be conducting in nature. So what was the question? Which is an exception in coal and solid for electrical conductivity. It is graphite. Okay, let us see the different types of arrangement. See, when we arrange all the constituent particles of a solid, whatever we have seen in three-dimensional arrangement of the particles in a crystal lattice as represented here. In case of an ionic compound, it would be sodium and the chloride ions. In case of a carbon dioxide, it would be the molecules. In case of argon, it would be argon atoms, anything of that type. So the three-dimensional arrangement of constituent particles in a crystal is represented diagrammatically, in which each particle is called as a point, or we call it as a lattice point. Wherever these atoms, ions or molecules are arranged, we call it as a points, or more specifically as a lattice point, and the complete arrangement we call it as a crystal lattice. And this smallest part, which is been given with this color, we call it as the unit cell. Unit cell is the smallest three-dimensional arrangement of crystal lattice, which will set the complete. See, if I know about this, I can know about the complete crystal structure. Why? It's because this is the smallest arrangement which sets the complete pattern. The whole thing we call it as crystal lattice, while the smallest part of it, if we study about that, we know the complete arrangement, we call it as an unit cell. Fine. Each point in the lattice is called lattice point or the lattice site. Represents one constituent particle, which may be an atom. In case if I take carbon, graphite, diamond, argon, a molecule, it can be like carbon dioxide, iodine molecule, anything. Or an ion, if I take up a ionic compound like NaCl. How do I get this three-dimensional structure? These will be very closely arranged like this, very closely arranged. If I try to pull them apart and then draw a straight line to bring out we get the geometry of it. These, so don't think that they'll be very close to, even very far away like this. They'll be very close. We try to pull them apart and then we get what is called as the geometry of the lattice. What is unit cell? Unit cell is the smallest portion of the crystal lattice, which when repeated in different directions generates the entire lattice. That is, you study completely about a unit cell of a particular crystal, you will know about the complete crystal. Now, what are the characteristics of a unit cell? You can see the three different axes are taken. See, this is an edge length which is called as A. The other side of the edge length is called as B, and here you find an edge length called as C. The distance between two corners we call it as an edge length, and they are represented by A, B and C depending on the axis. And the angles between A and C is represented by beta, between B and C is represented by alpha, and between A and B is represented by gamma. These we call it as interaxial angles, and these A, B and C represents the edge lengths. So we use 6 different parameters. We use 6 different parameters to explain about a simple unit cell. 3 we take it as edge lengths and 3 we take up the angles. Based on this, we have different 7 crystal systems. based on the relation between the edge lengths A, B and C and the interaxial angles alpha, beta and gamma. We have 7 different crystal systems. And how do I remember them? For C, it's easier to remember it as crazy teacher one day made us draw triangles, hexagons and rhombus. And it's easier to remember these one. So first with complete symmetry, let me go with axial distances. With cubic, A, B and C are equal. Tetragonal, A, B are equal, C is not equal to it. See, from complete symmetry, it's going to complete unsymmetry. That is, here, these two are not equal. I mean, it's must that we remember all these. And then you can see that again, we are ending up with complete symmetry. So let me go one by one. Cubic, the edge lengths are equal and the angles alpha, beta and gamma are equal to 90 degrees. In tetragonal, A is equal to B, B not equal to C. You can see an elongated one edge length. So A and B are equal, but it's not equal to C, but the angles are same. Alpha, beta is equal to gamma equal to 90 degrees. Let's go for orthorhombic. None of the edge lengths are equal. You can see the difference in the shape that is drawn onto the right side. But if you look at the angles, alpha, beta and gamma are equal to 90 degrees. Then let's go for monoclinic. Again, the edge lengths are not equal. What is the basic difference between orthorhombic and monoclinic? In orthorhombic, the angles are 90, but in monoclinic, the edge lengths are not equal. In monoclinic, alpha and beta will be equal to 90. Gamma is not equal to 90. Purijitama. Difference between orthorhombic and monoclinic. If you go for triclinic, again the angles are, edge lengths are not equal and angles are also not equal. So I can say completely unsymmetrical structure is triclinic. Then if we go for hexagonal, A is equal to B, not equal to C. Alpha and beta are equal to 90 degrees, but look at this angle, it's equal to 120 degrees. Trigonal or rhombohedral, A equal to B equal to C, but alpha equal to beta equal to gamma is not equal to 90 degrees. These are the 7 different types of crystal systems. How do we remember this? Remember this, recollecting this one. I mean, it's easy to recollect whenever you can learn it in this way and go from complete symmetry to complete unsymmetry till here and then start with symmetry. That is, what do I mean by symmetry and unsymmetry? All the edge lengths are equal, all the angles are equal. One edge length is not equal, angles we are still retaining it equal. The edge lengths are completely unequal, angles are equal. Then we will start changing the angles. First it's only gamma, then it's all different. So how do we remember it? Crazy teachers one day made us draw triangles, hexagons and rhombus. Rhombohedral we also call it as trigonal. Let's do a few questions on this. Which of the following crystal is represented by A not equal to B not equal to C, alpha is not equal to beta not equal to gamma equal to 90 degrees? What should be the answer? It is triclinic. Fine. Here let's take another illustration. The crystal system of a compound with unit cell A equal to 0.387, B is equal to, that is A is equal to B, C values different, so I can write A equal to B not equal to C, because they've given same edge lengths for A and B, a different value for C. Alpha equal to beta equal to 90, gamma is equal to 120 degrees. This is the question asked in 2004. So it's must that you remember those 7 crystal systems. There's every chance that they can ask you such questions. What is this arrangement? It is a hexagonal arrangement. Hope you understand it. Let's go with one more illustration. Pujita Amma. They're very easy. 7 crystal systems padicha podhu nammalku. For orthorhombic system, the axial ratios are given as A not equal to B not equal to C, and they asked us what are the axial angles in orthorhombic. So it should be alpha equal to beta equal to gamma equal to 90 degrees. You can see asked in 1991 as well. Let's check with the answer. Yes, answer is alpha equal to beta equal to gamma equal to 90 degrees. Fine. Thank you very much. Let's meet again in the second class of solid state. Thank you. హలో, నాకు ఒకటి అర్జెంటుగా వీడియోది మొన్న ప్రాబ్లం అయింది, ఒక లెక్చర్ దాని మీద కాన్సల్ట్ చేస్తా ఉన్నాను. ఏం లేదు, బాగానే ఉందన్న.